Okay, welcome back. This is the second installment of the chapter concerning acid-base, electrolyte, and fluid balance, and we're addressing here the regulation of calcium ions inside and outside the cell and throughout the body compartments. It's regulated within a narrow range. Remember, calcium isn't just important for maintaining strong bones, it's also a critical player in nerve transmission and also in the establishment of muscle contraction. As a result, if we don't keep a pretty tight lid on our calcium ion distribution, both of these processes are going to be negatively impacted. So elevated extracellular levels usually prevent membrane depolarization, while decreased levels lead to spontaneous generation of action potential. And if you think about it, remember that in normal conditions, right, the outside of the cell is positively charged compared to the inside of the cell. And so this completely follows, right? If we have elevated extracellular levels, then what's going to happen is that the polarization that exists across the cell membrane is going to be enhanced. It's going to be more difficult to establish an action potential. While decreased levels are going to reduce the amount of polarization across the membrane, and the likelihood of generating an action potential will go up dramatically. So the terms that refer to imbalanced calcium ion concentration are hypocalcemia and hypercalcemia. The major players here are a couple of hormones, well, more than a couple, but the two major players are parathyroid hormone, which is of course produced by the parathyroid glands on the back of the thyroid. Their action is to basically increase blood calcium levels, and also calcitonin, which is produced by the thyroid gland, which has the opposite effect. Okay, it tends to reduce blood calcium levels. In addition to this, PTH also decreases extracellular phosphate levels. One of the things that we don't want to do as we increase blood calcium, extracellular calcium, is increase phosphate levels at the same time, because we'll produce calcium phosphate salts, and those will be essentially difficult to dissolve. Vitamin D stimulates calcium uptake in the intestine, while calcitonin decreases extracellular calcium levels. So it's the interplay of these two hormones that's critical, again, in keeping your blood calcium within nice tight limits. And what you're looking at here are just, again, an example of what can happen when we have imbalances of this particular ion. Hypocalcemia can be caused by problems with either ingesting it or absorbing it. Okay, it can also result from a deficiency in the production of active vitamin D, and we can also have problems at the endocrine level where we have decreased parathormone secretion, and also, again, we note here malabsorption of fats, okay, which reduce the amount of vitamin D that we can take in, because remember, vitamin D is a fat-soluble vitamin. Remember, A, D, E, and K. Bone tumors can also increase calcium deposition, okay? So all of these can result now in a decrease in the amount of free calcium. And what do we see? Confusion, muscle spasm. We also see hyperreflexes, intestinal cramping, convulsions, tetany, inadequate respiratory movement, and prolonged cardiac ventricular depolarization. Essentially, what we have to appreciate here is the effect that calcium is having on action potential. Okay, and when we have decreased amount of calcium outside the cell, what's happening? Well, we're increasing the polarity, and the result then is going to be more difficult for us to initiate now an action potential, because now it's more difficult to get to the depolarized state. Okay. Um, on the flip side, when we look at hypercalcemia, this can result from excessive parathyroid hormone secretion or too much vitamin D. And here we see fatigue, weakness, lethargy, can also trigger anorexia, nausea, constipation, reduced cardiac ventricular depolarization, and can also obviously result in unfortunately, kidney stones, renal calculi, which we've detailed in class can be an extremely painful experience because it can occlude the flow of urine from the kidney to the bladder, resulting in intense pain and also damage to the organ. Magnesium is another one of those ions that's critical because it serves as a cofactor in so many metabolic reactions. And what we're looking at here is just, again, the same type of flow chart we've been peeking at for sodium and potassium. So here, what we see is a disturbance in homeostasis. Blood magnesium levels increase, homeostasis is disturbed, so what happens here is that the increased blood magnesium in the filtrate exceeds the kidney's capacity to reabsorb magnesium from the filtrate, and the result then is that we lose magnesium. Okay, the magnesium is not reabsorbed from the filtrate and it enters the urine, and the blood magnesium levels go back to their normal set state. Flip side here, okay, blood magnesium levels decrease, homeostasis is disturbed. What happens here is the decrease in blood magnesium levels cause the kidneys to reabsorb most of the magnesium from the filtrate, and then we restore normal plasma levels of this ion. Okay, here we're looking at table 27.9, and we're examining causes and consequences of magnesium imbalance. And what we start out with is a discussion of hypomagnesia, which is essentially low magnesium concentration. Causes include malnutrition and alcoholism, reduced magnesium intestinal absorption, problems with the renal tubule, and certain diuretics that can cut down on the magnesium concentration in the body. Symptoms include irritability, muscle weakness, tetany, and convulsions. Now, it might not be immediately obvious why these conditions manifest themselves, and this requires a little bit of consideration of the effects at the level of the pump and the channels that populate the membranes in the cells that are impacted by these changes in magnesium concentration. First thing we should note is that hypomagnesia triggers hypokalemia because it enhances potassium channel efflux and the elimination of potassium by the kidney. Okay, so one of the things that you'll notice in this series of physiological manifestations is that there's some overlap with what we would consider to be hypokalemia. Okay, so the reason for this, again, is, as it turns out, its effect on the sodium-potassium pump. So one of the other manifestations of hypomagnesia is to inhibit intracellular calcium release. This inhibits parathormone secretion, and this also triggers, by extension, hypocalcemia. And so we can see some manifestations of hypocalcemia in these symptoms as well. And finally, we should note that hypomagnesia slows down the sodium-potassium pump because it's required for pump function, and this causes an increase in potassium loss, and this results in tachycardia, basically the heart firing above its normal rhythm. So let's go ahead and note some of these. We'll indicate this in blue. Essentially, what we want to do is address what's triggered. Okay, and if we do that, we end up here with hypokalemia. We also end up with hypocalcemia. And decreased sodium potassium pump action. Okay, so an interesting cluster of manifestations just as a result of reduced concentration of this ion alone. Now, hypermagnesia is the flip side of this phenomenon. It can be caused by renal failure or exposure to magnesium-containing antacids. Symptoms include nausea, vomiting, muscle weakness, hypotension, and bradycardia, which, as you can imagine, are going to be related really to each other. The bradycardia will be in part responsible for the hypotension, and we also see a suppressed rate of respiration. So what you're seeing here, as opposed to manifestations of hypokalemia, are some manifestations of hyperkalemia. And also hypercalcemia. Okay. Next thing we want to talk about is the regulation of phosphate in the blood. Phosphate is an anion, and we are going to note that is relatively wide level of ranges, homeostatic range for this particular anion, but we still need to keep it tightly regulated. What is phosphate good for? It's a building block for nucleotides, for phospholipids. It's also important in the manufacture of DNA and RNA. Okay, so in addition to that, it has a major role in cell signaling. So if we start here with our homeostatic window, and we see blood phosphate levels going up, what's going to happen is that we're going to see increased blood phosphate, causing the phosphate levels in the filtrate to exceed the kidney capacity to reabsorb the phosphate from the filtrate, and the result is that it's going to enter the urine and be excreted from the body, and the levels are going to drop back to normal. On the flip side, if blood phosphate levels decrease, what's going to happen is we're going to see a decreased blood phosphate level, causing the kidneys to reabsorb most of the phosphate from the filtrate. The result is the phosphate levels in the blood plasma will climb, and we'll be back to homeostatic levels in a relatively short period. Okay, so if we're looking here at regulation of phosphate, under normal conditions, reabsorption of phosphate occurs at a maximal rate in the nephron. An increase in plasma phosphate increases the amount of phosphate in the nephron beyond the maximum, and so we excrete the excess in the urine. Note that hypophosphatemia is caused by reduced absorption from the intestine due to vitamin D deficiency or alcohol abuse, while hyperphosphatemia can be caused by renal failure, chemo, and hyperparathyroidism, which results as a secondary effect of elevated plasma calcium. So, what we're looking at here are some of the causes and the symptoms of phosphate imbalance. For hypophosphatemia, it can be caused by reduced intestinal absorption because of vitamin D deficiency or alcohol abuse or hyperparathyroidism. Symptoms include reduced metabolic rate, reduced oxygen transport, reduction in blood clotting, and reduction in white blood cell function. And this is in part due to a lack of DNA building blocks. Okay? Hyperphosphatemia, on the flip side, can be caused by renal failure or tissue destruction from chemo or hyperparathyroidism as a result, resulting in reduced renal phosphate excretion. Symptoms include formation of calcium phosphate deposits in the tissues, the lungs, kidneys, and the joints. symptoms of reduced calcium related to the formation of these deposits also results. And when we're talking about these deposits, we're talking about crystals. So this will contribute to, among other things, renal calculi. Bottom line, okay, important ion to maintain within homeostatic limits because of its role in signaling, its role in nucleotide production, DNA and RNA production, and also phospholipid production. Okay, this is just a diagram showing you how a strong and a weak acid respond to being dissolved in water, and also how a strong base responds to being dissolved in water. The bottom line here is, as you can see, a strong acid is always going to completely dissociate in water. The result is the production of large amounts of protons, and this is going to cause the pH to drop dramatically. With a weak acid, we don't have complete dissociation. The result is that fewer protons are produced and the effect on pH is minimized, while a strong base will completely ionize and the resulting hydroxide anion will scavenge protons from weak acids, among those being water itself. The result will be the production of water molecules and a reduction in proton concentration, and this will cause the pH to rise. So how do we regulate our acid-base balance? Remember that acids are proton donors while bases are proton acceptors. They can be grouped as strong or weak based on their ability to ionize. One of the ways that the body resists the dramatic pH changes that would otherwise be brought about by acid-base challenges is through a series of buffer systems. When protons are added, the buffer will sequester those protons in the context of a weak acid, which will not significantly ionize. When the buffer is removed, the buffer replaces it. When the protons are removed, the buffer replaces it. And what we mean by this is that when we throw a strong base in there, we will give a base challenge, what will happen is that the buffer will surrender its protons to the hydroxide anion forming water, and the result then is that we have turned now a strong base into a much weaker one, and the effect on pH is abrogated. Examples of buffer systems we see in the human body include the carbonic acid bicarbonate buffer system, also the protein buffer system, and the phosphate buffer system. So what you're looking at here is just an example of how acid-base balance is accomplished in the body. So if we take a look here at a change in pH, okay, and here what we're seeing is that the blood pH increases, so the proton concentration decreases. How do we bring now the pH back down? Okay, and we do this by a series of reactions that are going to acidify the blood plasma and by extension the tissue fluid. So what happens in the body is that in the blood we're going to now shift the equilibrium reaction that forms carbonic acid to the right. The result is going to be the production of more carbonic acid, which will result in the production of more protons, and this will have the effect of lowering the pH. In the lungs, what's going to happen is that respiration rate and depth will slow. The result is that carbon dioxide will accumulate in the body, and this will form now more protons as a result of this carbonic acid equilibrium. So what happens is the CO2 builds up, is that it's going to react with water more extensively, both as a result of the reaction being catalyzed by carbonic anhydrase, but also it's going to happen spontaneously in the blood plasma itself. And the result, again, is that the pH will begin to drop. What happens in the renal tubules is that we're going to secrete fewer protons. As a result, more protons are going to be reabsorbed back into the blood, and this is going to cause the pH to drop even further. Now, if we look at the flip side of this equilibrium, what we see here is a change in the pH, and what's happening in this case is that the pH is beginning to decrease, and so what we have to do is take action to elevate the pH. So what happens here is that we shift the carbonic acid reaction back to the left, and we do this by taking more proton and bicarbonate, forming carbonic acid, and what we're going to do to shift this to the left is we're going to blow off carbon dioxide. Okay, so as carbon dioxide leaves via the respiratory system primarily, we force this equilibrium reaction to the left, we consume protons, and the result is an elevation in pH. In the lungs, what happens is the rate and depth of respiration increase, and we blow off more CO2, and the result now is a reduction in proton concentration in the alveolar blood, and by extension systemic blood, and what will eventually happen is that the pH is going to begin to rise. What happens at the level of the kidney tubules is that we're going to secrete more protons. The result, again, is going to be an elevation in the pH of the blood, and as a result, the pH of the body tissue fluid. Now, buffers, remember, are capable of resisting acid-base challenges. If the pH rises as a result of a base challenge, the buffers will bind protons, while if the pH falls, the buffers will release protons, bringing the pH back down towards normal. In protein buffering, what we have is a range of capacity as a result, again, of the polar and charged amino acid residues that populate most proteins. Intracellular and plasma proteins can absorb protons, and they provide about 3/4 of the buffering capacity in the body. Examples of proteins that can buffer include albumin and hemoglobin. The bicarbonate buffer system is important in the plasma, while the phosphate buffer system is important as an intracellular buffer, and it also plays a role in the formation of urine. Okay, because of the secretion of protons, the phosphate components that are in the urine can buffer those changes in the filtrate and in the urine and result in less damage to the tissues of the tubule. The respiratory center also plays a role. If the pH rises, the respiratory rate slows, while if the pH falls, the respiratory rate goes up. And again, this is aimed simply at controlling the retention or the excretion of carbon dioxide. The more CO2 we blow off, the more we're going to elevate the blood pH. The less CO2 we blow off, the more we're going to drop the blood pH. And the kidneys, of course, play a major role. If the pH rises, the distal tubule decreases proton secretion into the urine and decreases bicarbonate absorption into the blood. As a result, more carbonic acid will dissociate into protons and bicarbonate. If the pH falls, the distal tubule increases proton secretion into the urine and increases bicarbonate absorption back into the bloodstream. Now, what you're looking at here in table 2711 are some of the characteristics of the different buffer systems that populate the body. And what I want you to do is sort of star this and note where these buffer systems act and how they do their trick. All buffer systems basically work the same way. They're all going to consist of an acid and its conjugate base, and when challenged then with an acid or base from the outside, what will occur is that the amount of free proton in the fluid is not going to change significantly due to the buffering effect, and the result is the pH shift will be minimal. So how does the respiratory system play a role in maintaining acid-base balance? Carbonic acid bicarbonate buffer system is used in conjunction with changing the respiratory rate in order to maintain the pH of the blood. As CO2 levels increase, the pH will decrease, while as CO2 levels decrease, the pH will increase. Carbon dioxide levels and pH are going to trigger respiratory responses. Hypoventilation is going to increase blood CO2 levels, and the result of increasing blood CO2 will ultimately be a decrease in pH, while hyperventilation decreases blood CO2 levels, and the result then is going to be an elevation in the blood pH, again because of that shifting carbonic acid equilibrium. Here we're looking at how the respiratory system and the cardiovascular system and of course the hypothalamus regulate these components. CO2 reacts with water to form carbonic acid, which is catalyzed by carbonic anhydrase that you find in erythrocytes. You also find this on the surface of the blood vessel epithelium. The catalyzed reaction is much quicker than the spontaneous one. The carbonic acid dissociates to form protons and bicarbonate, and an equilibrium is established. Decreases in the pH in the extracellular fluid stimulate the respiratory center and cause an increase in the rate and the depth of which you breathe. So you blow off more carbon dioxide. The result is a shift in this equilibrium reaction towards the production of CO2, which will by its own turn consume protons. And the result then is going to be an elevation in the pH of the blood back towards normal. So you can see how quickly the respiratory system can do its trick. Now, we should point out the fact that while it's rapid, the capacity of the respiratory system is limited compared to the urinary system. So we need to use these two systems in conjunction in order to adequately maintain body pH. Secretion of protons into the filtrate and reabsorption of bicarbonate into the extracellular fluid cause extracellular pH to go up. Bicarbonate in the filtrate is reabsorbed, and the rate of proton secretion increases as the body fluid pH decreases or aldosterone levels increase. Remember that aldosterone is your sodium retaining hormone. It also is your potassium secreting hormone. And remember that potassium and protons are basically swapped for each other. Okay, and that's one of the ways, again, that we maintain membrane potential while accomplishing the regulation of pH. Secretion of protons is inhibited when the urine pH falls below 4.5. The reason that we don't see more extensive changes in the range of urine pH is due primarily to the buffer systems that exist in the urine itself. What you're looking at here is just the renal regulation of acid-base balance. So if we consider when the filtrate or the blood pH decrease, protons are going to combine with bicarbonate and form carbonic acid, which will be converted into carbon dioxide and water. The carbon dioxide diffuses into the tubule cells. In the tubule cells, carbon dioxide combines with water to form carbonic acid, which then dissociates into protons and bicarbonate, again catalyzed by carbonic anhydrase. An antiport mechanism secretes protons into the filtrate in exchange for sodium from the filtrate, and as a result, filtrate pH begins to decrease. The bicarbonate anions are symported with sodium into the interstitium, and here they then diffuse into the capillaries. In the capillaries, bicarbonate combines with proton, and this decreases the proton concentration and ends up increasing now the blood pH. So you can see how this all operates. So the kidney has this unique ability to excrete these protons, and that's one of the major players in the regulation, again, of body pH. Now, how do we buffer these hydrogen ions? Hydrogen ions are secreted into the filtrate and they are buffered. They can react with bicarbonate and enter the filtrate to form carbonic acid, which is in equilibrium with water and carbon dioxide. The hydrogen ions can react with phosphate anion that enters the filtrate to form phosphoric acid. Hydrogen ions can react with ammonia to form ammonium cation, and all of this can be secreted in the urine flow. Remember that the buffering system is going to resist the pH challenge, and this results then in less damage to the kidney tubules, while at the same time accomplishing the most important goal, which is to maintain body pH. Acidosis is defined as the pH of body fluids below 7.35. Respiratory acidosis is caused by inadequate ventilation, reduced elimination of CO2, asthma, damage to the respiratory center in the brain, and emphysema. All of these result in a decreased efficiency of ventilation. The result then is CO2 begins to accumulate in the tissue fluid and in the blood plasma, and that ultimately results in a reduction in the pH. Metabolic acidosis results from all conditions other than respiratory that are going to decrease pH, and these include diarrhea, vomiting, and ingesting an overdose of aspirin. Untreated diabetes results in metabolic acidosis due to the production of keto acids as essentially metabolic byproducts that in and of themselves are going to reduce pH because they are proton donors. This is due to the fact that we can't completely oxidize fat without some carbohydrate intermediates. Also, anaerobic respiration will result in metabolic acidosis, and this is again due to the fact that we're going to tend to accumulate lactate as a result of only being able to run the first of the three legs of metabolism, that being glycolysis. Alkalosis is defined as a body fluid pH above 7.45. Respiratory alkalosis is caused by hyperventilation, where you're blowing off more carbon dioxide than you produce. The result is that we shift the carbonic acid curve towards the end that produces the CO2, and that's going to consume protons, and that's going to cause body pH to go up. Metabolic alkalosis results from all conditions other than respiratory that increase pH. These include severe vomiting, too much aldosterone, or ingestion of substances like bicarbonate of soda. What will happen here, again, is that the body pH will begin to rise, and the result, if unchecked, is that membrane potential will be perturbed, and eventually proteins can denature and the chemical reactions they catalyze can cease. Compensatory mechanisms such as the respiratory system and the urinary system act to try and maintain these pHs within this nice tight window. We should also note that the body buffers play a major role in this as well. The last slide here is just a summary of the conditions that produce acidosis and alkalosis. This is 27A in your text. Again, star this chart, know this material. This is excellent test material. Okay, that brings to an end chapter 27. Again, make sure and review the information in this podcast. It will be material that will show on a PRS quiz or on the exam. I'll see everybody in class. Good night.